I'll give a very short introduction. Hi, everyone. I'm Camille, but today I'm not going to talk, but Milou is. Milou did a 3-month internship with me, and she did very good research, I think, and she will present that research in this talk. So enjoy. Over to you, Milou.
Thank you, Camille. So I am Milou, and I'll be talking about green quantum computing for financial services. First of all, thank you all for being here. It's quite an honor to present for you all. The specific topic is a comparison of energy consumption between the use of quantum computers and classical computers for derivative pricing using Monte Carlo simulation. And throughout this presentation, I'm going to break this down for you. And I hope that at the end, you all have a clear understanding of what I mean with this. So I'll first give a short introduction to the topic, then I'll dive more into the financial derivative pricing and the classical and quantum algorithm used for this. Then we'll talk more about the energy consumption of a quantum computer compared to a classical computer. And then finally, some of my results of the internship and the conclusions we can draw from this. So first of all, quantum computer is a new way of computing with very high potential. It can have application in a large range of fields, as you've probably all heard of, ranging from life sciences, drug discovery, finance, and even climate change mitigation. So in general, it's perceived as a rather good technology. However, on the other hand, we've also seen the increase of energy consumption by information and communication technologies, which is currently estimated to be 11% of the global energy consumption. And specifically, data centers, artificial intelligence, and cryptocurrency have been in the news due to their very high energy demand. And we have this Paris Agreement to fight climate change and the urge to do so as soon as possible, which for me at least raised the question, will quantum computers be the next technology with controversial benefits? It can help solve problems related to the climate crisis, but also contribute to this. So first of all, a little introduction into quantum computing. So quantum computing is based on different quantum phenomena, called superposition, entanglement, and interference. And without getting into too much detail of this, what's important is that classically at the computer you have a 0 and a 1 state, whereas due to this superposition you can have a 0 and a 1 state at the same time, and everything in between those states, which is represented by this sphere here. This creates a new way of computing because you have all those states in between, and also uses the phenomena entanglement because you can create relations between two different states. So for example, if the one is always a 0 and the other one is always a 1, if you can state that one is always a 0 and that the other one has to always be a 1. So this combination of the two is what we call a quantum bit, also called a qubit. And as we are now able to perform calculations beyond the 0 and the 1 bits, we can create a speed up, quadratic to exponential based on the specific problem. This is to show you some of the physical qubit systems that are used nowadays for quantum computing. There's nuclear spin system, superconducting systems, and V-centers, a large range of them. Today we'll be focusing on superconducting circuits. It's not really important to understand the platforms, but just to give you a bit of an insight of what's currently possible. What is important is that to observe quantum phenomena within those systems need to be isolated. And in order to do so, this costs energy. So quantum phenomena are only visible in isolated systems with temperatures very close to 0. And as this is the case, a cryogenic system is necessary. So a system to cool down the system. which gives a very interesting relation with the energy cost, because we now have this big energy consumption due to the cooling costs, but quantum operations themselves occur at the electron scale, so they cost very little energy. Whereas for a classical consumption, these operations themselves already cost a lot of energy, and the energy cost scales linearly with problem size and complexity. So just to give you a little bit of an insight, this is what IBM envisions as their quantum system 2. This whole thing would be about the size of your room, and then this is surrounding electronics, and then somewhere in here would be the quantum computing cooling system, and then somewhere in there the very small chip that's actually the quantum computer. So if we now look at the energy cost, we would say that we have the cryogenic system, the electronic racks, and the supporting classical computer power that's required to drive the system. And this would cost about 25 kilowatts in total, which is similar to 25 households on average. So this is quite a lot, actually, to just drive one computer. But on the other hand, yeah, there's not much of scaling with the quantum level. So with the quantum level, I mean qubit operations, measurements, and also things like error correction codes. And there's not a direct relation, but what you can imagine is that if you go from 1,000 to 10,000 to 1,000,000, at some point you will require extra cooling, and you will require more electronic racks. So there's still going to be some relation between the two, and this is not very trivial. So this is what we'll discuss later throughout the presentation. The specific problem that we focused on was derivative pricing. This was discussed between Capgemini and financial institutions as a very relevant problem to reduce the energy consumption of. So what is derivative pricing? A financial derivative gives the opportunity, but not the obligation, to buy a stock at a later time. So you would have the strike price, which is the price of today, and then you might want to pay €5 in order to keep it at that price for the future. And the question is now, what should this price be? Should this be €5? Should this be €10? This then depends on what we expect the path of the stock to do. So the price of the derivative is determined by the difference between the expected price at maturity and the strike price today. That would be the fair value of the derivative. And there's different methods to do so, one of which is the Black-Scholes-Merton equation, which is a relatively simple analytic partial differential equation method. But when the market dynamics become too complicated, this way of solving it actually becomes unsolvable to solve with the Black-Scholes-Merton equation. So then often Monte Carlo simulation is used, and this is a simulation of a random walk based on the market dynamics. And this is actually what we will focus on, because there's a quantum algorithm for this. And this I'll also explain more in the section of financial derivatives. So what is important here is that previously we had this relation between accuracy and time for quantum computers. Running a quantum algorithm for longer will increase the accuracy, and using it for a shorter amount of time will decrease the accuracy. So there's a clear relation between those two. But now we also get a relationship with energy, because increasing the energy cost can decrease the temperature and therefore increase accuracy. At the same time, increasing the amount of time that an algorithm takes to run will also increase the energy, and decreasing this time will then decrease the energy consumption. So there's a very interesting relation here that we'll explore. Now, why is this all so interesting and so relevant? This is because we can see a potential energy advantage of pricing derivatives, because we have this classical Monte Carlo simulation that has a certain scaling of the error, and a quantum Monte Carlo simulation that scales differently, which leads to a quadratic speedup of the quantum algorithm. And energy depends on the power consumption of the quantum computer and the time. And this power consumption needs further investigation, but the time gives us a quadratic speedup. So this gives a potential for a quantum energy advantage. Yeah, so in general, my project was called the Olive project, which was based on the first thing that was used for derivatives, olives. And well, that's just the name, sorry. And the specific focus is on the energy consumption of a quantum computer versus a classical computer, and on pricing derivatives using Monte Carlo. Yeah, and because they're green indeed. And pricing derivatives using Monte Carlo simulation. And I'll first focus more on explaining the application, which is pricing derivatives, and then we'll dive deeper into the energy consumption. So, pricing derivatives. Classical Monte Carlo simulation is a simulation of random walks, and the solution of this is found by averaging over a large number of those random walks. So you just perform the random walk maybe 1 million times, and then you take the average, and that is your solution state. This scales with 1 over square root of n, where n is the amount of iterations that we perform this simulation. Now, there's a quantum computing algorithm for this, which is based on Grover's algorithm. I'm going to give a very quick run through of this, just to give you some feeling of what it does. First, the QUBIT register is prepared as always, and then certain operations based on the probability distribution are performed. So this really depends on what we expect the market to do. And the random walk is already directly implemented in this. Then amplitude amplification is performed. This is this is because the correct solution is encoded into the phase, but we can't directly measure the phase, so we need to amplify the amplitude to get the solution state also in the amplitude. And then when this is performed, in the end, we can perform measurements, yes, to find out what our option price should be, or derivative price. And what makes this so interesting is that this scales now with 1 over n. What does this mean? So as said, this gives a quadratic speed up. For example, if we were to acquire an accuracy of 1 over 4, 25%, classically we would have to do 16 iterations, but using quantum computing Monte Carlo, we would only require 4. This is not so life-changing, but if we look at more realistic levels of accuracy, for example, 10 to the minus 3. Classically, we would need 1 million iterations, whilst our quantum computing algorithm would only require about 1,000. So that is a huge advantage and a huge difference. So the algorithm that I just showed was actually also run on first a quantum simulator and then an actual quantum computer. And these show the results of the quantum simulator. So we can see with the red line, that's the price that's estimated using the Black-Scholes Merton method, which is still very accurate for those simple derivatives. But with the quantum computer, we get those blue bars out. And then what we can see is that increasing the amount of qubits leads to a more and more accurate result. However, increasing the amount of qubits also comes with higher hardware requirements. So for the first time this was actually performed on a quantum computer, this was only done for the NS3 case, so with only 3 qubits. I'll continue. Thanks for your time here. So we saw that we have those results of the quantum simulator. We have NS3 qubits that we can use. And now this was actually recently performed on a real quantum computer, the IBM Q Tokyo computer. And the results are shown in this graph. The blue line is what would be the exact solution. And then the green triangles are based on maximum likelihood estimation, which is a method to reduce the hardware requirements slightly without error mitigation, and then the purple ones are with error mitigation. And we can see that first the error rate of 60% is achieved, and this can be reduced with error mitigation to 20%, which are still very high error rates, but it shows that this is really possible in practice, but not very relevant. Like, it doesn't have real applications yet, but the first, it's being done for the first time, which is really cool, I think. So we can conclude that this algorithm can actually be performed on a real quantum computer, although with very high error rates. Now to continue, I said this very shortly, but maximum likelihood estimation was used instead of phase estimation in order to reduce the hardware requirements. And similarly, error mitigation can also be used to reduce the error rate. And these are classical adjustments, but they don't really take away anything from the quantum algorithm. The quadratic speedup is preserved here. Now, recently, a new framework has been proposed called the KP framework that actually allows something new, which is to interpolate between the quantum and the classical algorithm. And what you can see here is that instead of, for a normal quantum algorithm, you would have no speed up until you at some point acquire a certain possible logical depth, which is a certain hardware requirement, and then you achieve a maximum speed up. And using the KP framework, we can actually already, based on using some classical power and some quantum computing power, we can interpolate between the two and create a partial speed up at lower hardware requirements. So we get this trade-off between speed up and hardware requirements. And this now looks very nice, but in fact the time it takes a quantum operation is still way longer than a classical operation. So we don't actually already acquire a speed up, but we might first have a slowdown and then slowly go towards a speed up. But either way, it's very interesting to be able to use this interpolation between quantum and classical algorithms, taking into account the clock speed of a quantum computer. Now, based on this quantum clock speed and the effective error rate, a recent paper published some possible scenario of how this would go in the future. And the gray area shows that it's infeasible to run good calculations on the quantum computer, but by increasing or decreasing the quantum clock speed and the effective error rate, slowly it becomes possible to run those algorithms. And this first leads to a slowdown, and then which is the red area, and then there will be a partial speed up shown by the light blue area before achieving the full speed up, which is the dark blue area. And currently we're in the left upper corner, so the infeasible region, but by improving the hardware requirements, we can get to the right bottom corner, which would then gives us the full speed up. And what's interesting about this is this light blue area where we now have a partial speed up at hardware requirements, where previously we would only get a slowdown. Now, this speed up depends on the complexity of the derivatives. So we have simple derivatives, which have a relatively short infeasible region, but this becomes larger and larger based on the complexity of the derivative. Yeah, so that was that about the financial derivatives, and I'll continue with talking more about the energy consumption now, and then in the end we'll combine those two. So the energy consumption of a quantum computer. As said, the most energy is acquired by the cryogenic system and the electronic racks. And this is the 15 to 25 kilowatt here is the power consumption. And what's actually very crucial here is that the quantum computer is always on. So starting up the quantum computer takes about 1 week, and then because of this, afterwards the quantum computer will always be on until some maintenance is required. But this means that we don't only have the power consumption when we run calculations on the quantum computer, but we have a continuous power consumption, which is very high. At the same time, the scaling does give opportunities because more calculations do not necessarily increase the amount of energy, and also increasing the amount of qubits or the circuit depth does not increase energy. So we can see that we have this macroscopic cost that's very big, but the quantum level doesn't really affect it. Now that's for how the current energy consumption looks. For the future, we expect something different, because in the future we would envision that quantum computers run calculations based on cloud computing so that everybody can perform calculations on them, and we have a continuous stream of calculations on the quantum computer. This also means that now the energy consumption does start to scale with the calculation time of your algorithm. At the same time, the power is also expected to increase with the amount of qubits and operations, because when you go from 1,000 to 1 million qubits, you can expect that you would also require more electronics. And those electronics will then also lead to more heat dissipation, which will increase the cooling cost. And at the same time, the electronics also require a certain amount of volume, and therefore the cooling volume will also be increased. So this all results in some scaling of the cooling costs. So now we can see that the macroscopic cost in the future will be in some way related to the quantum level. This is a visualization of how such a quantum computer system would look like. So you can see that the signal goes in from the classical computer, and then a large range of electronics and different temperature stages is used to finally do something at the qubit stage, at the quantum level, and vice versa, before the result is sent back to the classical computer. This image is quite complex, and it's not important to understand everything about it, but it's good to show you that how the electronics sort of look alike, and that there's a lot of different parameters in this system that can actually be optimized. And that's what a recent paper does. That's also based on this model specifically. It uses different parameters, so temperature in this case, attenuation of the electronics, and the level of quantum error correction, in order to optimize the power consumption of the quantum computer, whilst at the same time retaining its accuracy and performance. So you can see, so based on that, the graph on the left is found, and this gives an estimate of the power consumption based on the logical depth and the number of logical qubits. And this is very interesting because those are algorithmic parameters that can be used for any quantum circuit, because it's based on general estimations on quantum circuits. And you can see that there's some jumps here, which is due to the optimization of the error correction code as well. So those are different layers of quantum error correction. And in this specific paper, this is applied to the RSA encryption algorithm, which is an you may have all heard of, but in general, it's a way of encrypting a message safely, and the number behind RSA stands for the amount of bits used to do this. So the higher the amount of bits, the higher the complexity to break this code is, and the higher the complexity of your algorithm is. So you can see that, yeah, the power consumption also increases with complexity, which is then, yeah, so this graph is important, first of all, because the power consumption, it's general power consumption of a futuristic optimized quantum computer. So we can use this for some estimates of our algorithm as well. And then at the same time, what the authors show here for the RSA algorithm is also very interesting, because they actually show that a quantum energy advantage is possible. So to estimate the quantum energy consumption, the power is used from this optimized quantum computer model, and the time is used from the different scaling between your quantum and your classical algorithm, which is in this case exponential. So you can see here on the right that the classical computer scales differently with time than the quantum computer, and at like lower complexity level, lower bits of the RSA code, your classical computer would be way more efficient, but at higher complexity, your quantum computer becomes way more efficient. And this is then used combined with the optimized power consumption to make an estimate of the energy efficiency. And what we can see here is that, yeah, so for higher complexity, at some point the quantum computers become more efficient, but also by optimizing this power consumption, there's actually a region where the quantum computer might be slower than the classical computer, but still more energy efficient. And this is, I think, for me, this was a very surprising outcome and a very interesting outcome as well. And it really shows the possibility of using the quantum computer for a quantum energy advantage as well. Now, it is also important to note here that this paper was based on futuristic hardware numbers of the quantum computer, and also on, for example, optimized electronic efficiency. So it's, yeah, that's important to just take into account that this would still be required in order to actually achieve this in the future. So let's continue with the results section of the energy consumption of pricing financial derivatives. I'll first say something about the scaling of the power and the energy consumption specifically. Then I'll give some current estimates, and then I'll we'll discuss a future scenario that we expect based on this. So, as said, quantum computing Monte Carlo gives a quadratic speedup, and because of this, we also expect the energy consumption to scale accordingly. So we, you can see here the green line, which is the quantum computer, and the red line, which is the classical computer. And the classical computer scales quadratically with the accuracy, whilst the quantum computer scales, or the error rate, linearly. Which means that at low levels of accuracy, the classical computer would be the most energy efficient, whilst at high levels, the quantum computer would be the most energy efficient. This is not all, because in reality, the relative power consumption and the clock speeds matter a lot. So what this essentially means is that if the clock speed is very low and the relative power consumption is very high, will stay very much on the left of this graph, which is what was visualized here. And in this case, that would mean that even if you go to very high levels of accuracy, your classical computer would still be more energy efficient. But when we can decrease the clock speed and really optimize this power consumption, we can create a different scenario where instead the quantum computer might always be more energy efficient, which is what's visualized in this graph. For those graphs, we use a constant power consumption. And as said, we expect 2 different stages in this power consumption. So the first is what we call the research state, where we have a very high power consumption, but it doesn't really scale with the system size. And at some point in the future, the application stage will start to appear where the power consumption does scale with the system size. And based on the paper shown before, some linear scaling on the amount of qubits and circuit depth is expected, which is shown in this graph. Now, to specifically apply this again to the financial derivative pricing, we did a very small case study, which gives some current numbers, where we used a quantum computer and compared this to a classical computer for pricing a very simple derivatives on today available hardware systems. So we used the IBM quantum computer and we run the Grover script and then use this for an estimate for the option pricing. But as said, the option pricing is really possible on the quantum computer as well. And for the classical computer, we used a standard Python script and did it on a standard laptop. So that's also where we based the power consumption estimates on. We could measure the run times with those algorithms, with those systems, and then find the power consumption. And with some estimate of the clock speeds, we finally come to an energy consumption. And what you can see is that the classical computer is way more efficient than the quantum computer at this point, which shouldn't come as a surprise. The quantum computer is still very much state-of-the-art research and very upcoming. But this would say that it's a million times more efficient to do your algorithm on a classical computer. However, we can use the model presented before to make some future estimates, which is what I've done here. Based on the complexity of our derivative, we can estimate the amount of logical qubits and logical gates required and make an estimate of the power consumption that this requires, which is shown here. And then based on the clock speeds, we find the energy consumption that this would approximately use. What's important here as well is that if I go back to the power consumption it shows now is lower than what's available on current hardware. But as said, this is again an optimized quantum computer, so that's why this occurs. To continue with a future scenario, we presented the KP model, and where we saw this infeasible region, the region with no speed up, partial speed up, and full speed up. And on top of that, and we can translate this to the energy efficiency or the energy advantage. And here we similarly expect a region that is infeasible to run the calculations, then a region where there's no energy advantage nor a speed up, then actually a region where there might be an energy advantage without a speed up, a region where there's an energy advantage with a partial speed up again and a maximum speed up. So what's interesting here is that this green region is really a new insight, that we can acquire an energy advantage without a speed up, and also that we can use the KP framework to get a partial speed up and a partial energy advantage. This combined leads us to believe that there's 3 different phases that the quantum computer or the derivative pricing using Monte Carlo simulation on a quantum computer will go through, which is the research and development phase, the partial quantum advantage, and a full quantum advantage. Now, the research and development phase is what we're currently at. It has very high energy costs, and but at the same time, there's going to be a large improvement of hardware and algorithms in order to make to decrease this energy cost and to make this quantum speed up possible. In terms of the algorithms, the most improvement is required for quantum error correction and the quantum and classical integration or trade-off that we've talked about. And this will, in the end, have the largest effect on the energy, on decreasing the energy consumption. At the same time, we believe that during this phase, it's already very important to make conscious design choices for designing the future quantum computer. And this requires an interdisciplinary approach, which then requires optimization based on resource requirements as well, so that you can optimize your system based on decreasing the power consumption. At the same time, specifically for derivative pricing, this is a preparation phase for financial institutions. It's already important to prepare themselves and to investigate toy models of derivative pricing on a quantum computer in order to prepare themselves for the next phase, which is the partial quantum advantage. The partial quantum advantage can start off with being either computational or energetic, and this really depends on the hardware development and the investments and improvements that are acquired in the first phase. So for both, we expect to be able to use a trade-off between the classical and quantum algorithms based on the KP model. And we can also optimize this trade-off to reduce the resources. For financial institutions, this means that the first real calculations for simple derivatives can be done with this partial speed up and energy advantage. And it also means that if we actually acquire the energy advantage first, for financial institutions, certain calculations might already become interesting to perform on a quantum computer. So we had some discussions with Rabobank about this, and one example would be overnight portfolio calculation. So there are certain calculations within financial institutions that are able to take a little bit longer, but that for them it's not bad if it takes a little bit longer. So you could choose to run it on a quantum computer based on its energy advantage, even if it takes a little bit longer. That's what we're trying to say here. And then in the end, ideally, we reach the full quantum advantage, which means that the full computational advantage is acquired. So we have this full speed up, meaning it is now most relevant to price complex derivatives on the quantum computer, as they classically also have the highest power consumption, and therefore the most gain is acquired here. The same actually applies for the energy advantage. And what's also interesting is that because of this computational advantage, we can now do a way larger range of simulations and applications, for example, in climate modeling. However, this also means that the Jevons paradox becomes a thing, which is what is shown here. The Jevons paradox describes that when a technology gains efficiency, it doesn't decrease the overall cost, but it actually increases the overall cost or usage. So here you can see specifically for fuel efficiency, it tends to increase, which means that it doesn't decrease, but actually decrease fuel usage. And in order to avoid this, for the quantum computer, an interdisciplinary initiative is required, and some rules and regulations must be set up to ensure that quantum computer will be used for really this energy advantage, and not just higher efficiency and higher usage of this technology. So finally, the conclusions and the outlook. What we saw was that quantum computing today costs a lot of power and energy. And in the near future, using hybrid quantum classical systems we can expect to acquire the first gains in both the speed up and the energy consumption, and further investigations of this interpolation of energy costs is required here. In the future, there is a high potential for this quantum energy advantage, even without the quantum speed up, but this certainly is not a guarantee. We really need to focus on making the right optimization choices, the right design choices, and take this into account with every step in this journey. But although it's not a guarantee, I believe that there's high potential for this based on interdisciplinary research and the design choices. Also because there's currently a quantum energy initiative set up, which is a collective of the quantum computing community that's working towards this, and that really wants to make this possible and make quantum computing a sustainable, energy efficient technology. And this relates to the last point, which is that in the future, this should also be extended to other resources. So not just making the energy more efficient, but also looking at material choices and so forth. Then finally, some implications that this has for financial institutions. This is based on some discussions we've had with Rabobank and our own research. It's important for financial institutions to identify critical hardware parameters to make this energy advantage possible and follow the trends, as well as invest in the critical ones. At the same time, it's what we saw is really important to have some general methodology to benchmark both classical and quantum algorithms to make it easier to compare them, specifically based on energy consumption. The right implementation of quantum computing requires a social technical team at those financial institutions, in particular to stimulate this quantum energy advantage and also to avoid the Jevons paradox. Then it's the first usage will be hybrid quantum classical computer systems. And in the end, we expect that financial institutions will be able to use quantum computing also for the energy advantage for their financial calculations. And to close off, there's also a statement made by the managing director of JP Morgan, which states JP Morgan has made a plan to become a company with zero carbon impact by the end of this decade. Quantum computing can significantly reduce the carbon impact by being so efficient and allowing computations to be executed in a much shorter amount of time. So to me, at least, this shows that companies such as JP Morgan and Rabobank are really invested in reducing their energetic footprint, and quantum computing can help them with that in the future. So that's my presentation, and now I would like to open the floor for questions. And thank you all for listening, obviously. And also a special thanks to Camille de Valk, my supervisor, and other relevant people, but specifically Camille, because it's been a pleasure to work together on this topic.
Thank you. It was great working together for me as well. Are there any questions? I think I saw Cos raise his hand.
Yeah, no, sorry, I just misclicked. I wanted to do the applaud emoji, but apparently I'm too old for this. Nice presentation, though.
Thanks, though.
See a question from Kirill coming.
For an excellent
We cannot hear you yet.
Now we can.
Can you hear me?
Yeah.
Pardon. Thank you, Camille, and thank you, Milo, for an excellent presentation. My question, I actually have two questions. So first one would be, it would be really interesting to have a look on the other hardware. For example, I don't know, there are we hope there will be one day like photonic circuits which do not need probably that much cooling or semiconductor stuff. So there is plenty of things to do. And so looking forward to have another presentation in a few years about energy impact of other technologies in quantum. So if you have already something to say about other technologies of quantum computers, would be really curious to know.
Yeah, so in general, there are quantum systems being investigated that do not require this high cooling system. I think if you look at the near term, the most relevant systems and the systems that have the highest potential are the ones that do require this high cooling cost. So, I mean, in an ideal scenario, we can perform quantum computing at room temperature, and we then have very low energy costs because those quantum operations themselves, they require very little energy. So that would be ideal. I think realistically, looking at quantum phenomena, they do really need to be isolated, and temperature is such a big thing in that. It's such a like decoherence mechanism that has such a high influence that I think this cooling cost will, at least for the coming so many years, be a large thing here, unless some new breakthroughs come through, and that would be amazing. But yeah, I think realistically, looking at quantum computers, we are going to need this cooling cost. Also because there's some quantum computing algorithms that run at high temperatures, but then they're not gate-based quantum computing. So that would mean that only very specific problems are, they can only be applied to very specific problems to solve. Does that answer your question?
Yeah, perfectly. Thank you.
Thanks.
You had a second question, right, Kirill?
Yes, but I can leave the floor to other questions and ask it at the end.
Okay. I saw Mark also raising his hand.
Right, thanks. Brilliant presentation. Thank you. It's actually I learned a lot, especially about the financial side of this. Did you? I didn't catch whether you stated it, but did you actually have an idea of the number of qubits that were required to actually do an essentially a decent job? I'm not really talking quantum supremacy, but are we talking thousands of qubits, tens of thousands of qubits, and maybe the number of gates as well, if you've got that idea?
Yeah, so this is what I showed on the
It was one of your early graphs. Sorry, in that case I missed it because I joined late.
No. This slide. So here you can see that the amount of logical gates and logical qubits, depends on the. Why isn't it? Yeah, it depends on the complexity of your derivative. So for a very simple derivative, you would require about 10 qubits and then 1,000 logical gates to give a good estimate. What's the case here is that those derivatives are also very easy to compute on a classical computer. So the most interesting is really those complex derivatives that require also a lot of qubits and gates, but are still expected to be more energy efficient and have a very high speed up compared to how this is classically done.
Okay, that's brilliant.
So these are some numbers. Yeah.
Okay, that gives a good idea. Would I be, if I wanted to just get a back of the envelope feel for how effective this would be, would I assume that the fidelity of result, the signal to noise ratio, for want of a better word, would be something like found by 0.99 to the power of these number of qubits, or is there a rule of thumb that you came across? The sort of levels of error correction.
Yeah.
As a guess.
Yeah.
is-
So this whole model that's being used here, it reduces the resource requirements for a specific performance.
Mhm.
So this could be fidelity, and then you look really at the quantum level. But it's in this case it's accuracy, and I'm not, or like I'm
It's okay. We can.
I'm not sure which percentage they use. I think something like maybe they use 2/3.
2/3. Okay. That's.
Don't know this by heart,
fine.
but it's in the paper for sure. But I think
Oh, okay. Okay, brilliant.
Yeah.
Thank you. Thank you.
I just put the paper in the
Yeah. I
the
see
chat.
it. Thank you.
Yeah, what I'm trying to say here is
Yes.
what I show here is that you really first choose what you want as your minimum fidelity or your minimum accuracy
Mhm.
rate, and then you optimize based on that. So you choose some minimum, and then you can
You do that. Okay.
reduce your hardware, well, not your hardware, your energy cost based on that.
Okay, great. Thank you.
I think by looking at the time, we have to close it off here. I want to thank you again, Milou, for the great presentation. If there are any other questions, please feel free to reach out to me or to Milou.